let's get started. Okay, so today we are gonna cover more inverse RL. So last time we talked a little bit about what the formalism is. We're gonna recap that, and then we're going to go into two basic ways of doing inverse RLs. First is max margin planning, and the second is maximum entropy IRL. And then we're going to try and show how max entropy IRL is very, very closely connected to generative adversarial networks or GANs. So that's going to be our outline for today. Cool. So the problem of IRL, inverse RL, is the inverse of the RL problem, as named. But basically, it says that, hey, the reward doesn't appear magically in most settings. You have to set it. You can do that either by engineering the system, right? Or you can say, I'm going to get this automatically. So most people, or many practitioners right now would engineer the system. So they like have a bunch of things that think are relevant to the reward, and then they tweak them and add bonuses and do fancy complicated things or use LLMs to generate rewards. But the premise of inverse RL is a little bit different, right? So the inverse RL is trying to get away from this manual tweaking and specification. There's something that looks more like this, which says that you're given access to the environment, but no reward. You're given some set of expert behavior, close to expert behavior, series of states and actions, right? And then you're going to try and do this process of inverse reinforcement learning, or IRLs. IRL is going to give you some guess at this reward function, and then you're going to re-optimize that to get your policy, right? So the premise of the inverse RL is rather than doing reward tweaking, you're going to assume access to a reward-free environment, access to some set of demonstrations, and then we're going to try and find the reward that best explains those demonstrations. And so we have to assume something about the data, otherwise it's underspecified problem, right? And so we're going to assume that the demonstrations are close to optimal. We're going to find the rewards that explain these close to optimal demonstrations. And then we're going to try and re-optimize policies. So why would you do this? Why would we ever do this? Seems complicated. As you were saying, it's just like because reward tweaking is hard, but we did behavior cloning, right? So if we did this, why would we ever do inverse RL? Do behavior cloning. It's easy, it's offline, no RL in the process, no rewards needed. Dealing with covariate shift, right? So behavior cloning has this compounding error problem, RL won't. Are there other reasons? You can generalize better, right? And so the hope is that your reward is more compact. So it tells you that not that you have to like go in this particular path, but rather that you want to pick this thing up. And so you can generalize that to new dynamics, new settings, new initial states, and so on. And so the premise of inverse RL is that it's somehow more compact and more generalizable than just learning a policy with imitation. Okay, so the setting we're going to assume is that in reinforcement learning, you know your states, you know your actions, you don't know your transition dynamics, but you can sample from them. Your reward is known, but your expert policy and expert trace are unknown. Can you say that? Simple, I guess. It's hard to quantify simple, but like one way of thinking about it is it's like if I had to write a program to describe it, the program that describes the reward is shorter than the program that writes the policy.
Oh, so it's not like other compactness in like that.
No. Compactness in the information theory sense. So it's like simplicity, like you could think of it as like how much information is in that function. So you could, one way of thinking about it is through this like lens of Kolmogorov complexity, which is like, what is the shortest program that can describe it? And so the reward program is expected to be shorter than the policy program. It's not always true, right? You can like have a somewhat complicated reward function and the answer is to always go left. Like that's the policy. But you could also have like a complicated policy and a really simple reward function. So like picking this thing up is like a complicated policy, but the reward is very simple. So yeah, I wouldn't say it's like very, very precise, but I guess it's in many cases that's true. So an interesting research question would be to like properly characterize when policies are simpler than rewards and when models are simpler than policies and rewards and try to understand the connection between them. I don't know the answer. So RL assumes that reward is known, but your expert policy is unknown and you don't have expert traces. Inverse RL assumes that the state action transition dynamics are the same, but your reward is unknown. Your expert policy is unknown, but you're given some number of traces from an expert, right? So by traces, I mean trajectories drawn from an expert. So the premise is that you're going to try and find the reward function R, or the parameters of a reward function R. So you're going to try and find a function that maps from a state to a scalar that best explains the demonstration behavior, those demonstration traces as noisily optimal, right? And so you want to say that under my reward function, if I like re-optimize my reward function in these settings, I would get back the demonstration traces. And so it's inverse RL because you're trying to say that you propose a reward function, then you do RL, then you see how good that, like the result of RL is compared to the demonstration trace, and you have to invert it to find the best reward function, right? And so the goal of inverse RL is to get your reward function R fail. Then in a new setting, let's say you change your initial state distribution, let's say you change your dynamics, you can run RL to get a policy. So an often practical way of doing inverse RL is you learn a policy and you learn a reward function, and then you like improve the reward function, improve the policy further with inverse RL on top of behavior cloning. So you don't need to do that second step from scratch. It's just that this reward function is helpful to continue improving beyond your initial station. Okay, so why is this hard? What makes it different? Multimodality, yeah. So you have multiple reward functions that could explain the behavior. So like, for instance, to pick this thing up, there's one reward function, which is this thing is lifted. The other reward function is your hand goes in this trajectory. The other reward function is you go to the right of this thing and go to the left of this. Is like an ambiguous problem. What are other reasons that might be hard? Yeah.
Can there be like some connection between like the expert demonstration, like not capturing enough to like give you the right reporting?
Yeah, it's similar to Seth's point in that it's like if I don't have enough data, there remains inherent ambiguity in my reward function. And then if I just got one demonstration of this in one setting, it's like there's many things I could explain. So it comes down to the same underspecification. The other problem is that so it's inherently underspecified, like both of you just said. You often have a difficult optimization problem because you have RL embedded inside inverse RL. Like if I have a reward function, how do I know how good it is? I have to run forward RL, and then after forward RL, then I compare it to my demonstration traces. So embedded inside inverse RL is forward RL, which is what makes it a pain. And you don't know how to compare your expert traces to your reward functions. And so it's just like an underspecified problem. So you're asking why is inverse RL used? Kind of, but it's often a difficult optimization problem. But some of the things we'll talk about today will make it easy, right? And so that's the basic outline of inverse RL. And let's try to formalize it and kind of go through it a little bit. Questions before we go? Okay, so a basic template for the inverse RL algorithm is the following. You propose some reward function, R phi, right? So phi is your parameters of your reward function. Then you try to optimize a policy against your R phi. So you do RL against R phi. And then you try to compare the expert policy you get from R phi against your expert traces. And then you go and say, okay, this gives me some signal on how to adjust my reward function. I'm going to go back, adjust my reward function, and repeat, right? So the process is propose a reward, do RL, see what the result of RL was, how similar it was to the expert demos, go back, change your reward function, repeat. And so how do we actually instantiate this? And that's the question. Okay, so the first way we're going to instantiate this is we're going to be extremely simple, right? We're going to first start with a reward function being linear, which means that let's say we had some features phi SA of state and action. We're going to assume that our reward is linear in those states and actions, and we'll make it nonlinear from there. So let's start with something that's linear. So a reward function is linear. And then we are going to start by assuming we know the dynamics of the system, right? So we're going to assume that we have known dynamics, you have something linear. And then we're going to try and figure out how to instantiate the rest of this group. So how do we actually compare things to the expert traces? How do we get a reward function from there? So, okay, so with this in mind, so you have a linear reward function. You're given some expert demonstration traces. You're given the environment. There. What is a good reward function? Like what characterizes a good reward function? So what we know is that the demonstrations are optimal. Right? So if I have a reward function, what makes a reward function good?
If I optimize the reward, I should get value similar to the expert.
Right? So that's one way of doing it. A potentially easier way of thinking about it is also a reward function. Like even if you don't want to re-optimize everything, and a different way of thinking about it is a reward function is a good reward function is something that scores optimal data higher than all the other data, right? So it says that under my reward function, my value for my trajectories from my expert would be higher than the value of all other policies, right? So what that says is that under my reward function R, my value of pi star is going to be higher than my value of all other pi, right? That means that like essentially if I like optimize my value function for the best pi, I would get that pi star. And so if I can say v pi star r of s is greater than v pi r of s for all pi and all s, then that is a good reward function. Because it scores, like the only information you have is that the expert is optimal, right? And so this just says that under your reward function, the expert is better than every other policy. Right? Okay. So we're going to try and simplify this a little bit. Right? So we're going to start with this value function. And so if you remember the definition of a value function, it's going to say, if you remember the definition of a value function, it's saying that you have the expected sum of rewards under your pi star, right? And you have expected sum of rewards under pi. And expected sum of rewards under pi star is going to be greater than expected sum of rewards under pi for all s. Yeah. And so the nice part about this is because our reward function is linear, right? We can write this as expectation pi star of sum over t, gamma to the t, w transpose pi, stat, right? And similar on the other side, expectation of pi, sum t, wt, phi, right? So just substituting in a linear reward function. Now, what do I know about linear functions and expectations? Can I simplify this? Yeah, so it's linearity of expectation, right? So when you have a linear function, you can take it out from an expectation, right? And so this simplifies to something like W transpose expectation pi star, the sum of gamma to the t phi stat. And the right-hand side simplifies to W transpose expectation pi sum pi stat. Right? And so all we did is we took the W out on both sides, right? Just via linearity of expectation. And so the point here is that you can write this as linear. You can take the linear thing out. These things are often what we call feature expectations. They show up a lot in general RL research, but basically you can kind of think of it as rather than taking the expected sum of rewards, you can just take some arbitrary features, some vector valued features, sum them up over time, right? And then you can say that your values are linear in these expected features. So you can call these, let's call them mu pi star and mu pi, right? Yeah. That's it.
Is it always valid to assume that it's going to be a linear combination of features?
No, under our assumption of linearity of the reward.
Okay.
And so if the reward is not linear, then you can't do that. Right? We push. So under the assumption of linearity of reward, we can say that these are expected features under pi star. These are expected features under pi. And we want W star of expected features under pi star to be greater than or equal to W star of expected features under pi, where W completely characterizes your reward, right? So our parameters of our, I think I like overrode the notation a little bit, but think of the parameters of your reward function not as phi. Phi is given to you, those are features, but as W, right? So our reward function is, our goal in inverse RL is just to figure out what W is. Like it tells you like there's different features, like one of them is distance from here to here. One of them is like how far the block is lifted. One of them is like, is the gripper closed or not? And you want to find a linear combination of those features that gives you a reward. And so the condition for inverse RL is that W star times expected features under pi star is better than W star of expected features under pi for all pi. Okay? Does that make sense? So this is kind of telling you, you can kind of think of this as something that is describing like what are the outcomes under a trajectory. And it's gonna say like if I took a cumulative feature of the trajectory, what are the outcomes in terms of the sums of features that I get? And I want this W star, which is like my reward, to judge these trajectories as better than these trajectories. Okay, so that's the first thing. What the? That's the first thing we did. So this seems reasonable, right? So if I can solve this constraint, then I will find the best W star.
So quick question, is this just a thought experiment or do people really calculate these fees?
You often calculate these fees. So you can actually calculate fees just with TD learning. So you can think of like doing Q learning or something like that. You just replace R with fee. So you can do the Bellman update with fee, and you can compute these feature expectations often. The other way you can do it is you can just roll out trajectories and sum up your fees.
And do people tend to hand design these fees?
They often hand design these fees. Yeah. And so we'll build up to a method which goes from perception and a neural net without these fees. But until like, I'd say early 2010s, people were doing, or 2014, 13, people were like hand designing fees.
So this is our objective. Then what stops the model from learning a trivial reward function? Like for example, if W is all zeros, then this is technically true.
Nice. Yeah, no, you got it. The problem with it is that, as Michael just said, it has a trivial solution, right? So W star equal to 0 trivially satisfies them. And so just solving this constraint, like trying to find a W star that satisfies this constraint doesn't really work because you will instantly get a trivial solution, right? Okay, so this is our problem. How might we fix it? Our problem is that this constraint seems to make sense. We want to score this thing higher than every other thing. How do we do better than this trivial solution?
Can you put a constraint on the norm of the use power, like make it equal 1?
Yeah, exactly. So that's essentially what we will end up doing. But another way of thinking about it is through the lens of how many of you have heard of SVMs? SVMs, yes, more or less. No? Oh, sad. SVMs are good. Everyone should go read up on SVMs. But the idea is you essentially have this ambiguity problem, like W star equal to 0 is not the only solution to this, right? There's also like the true solution is also a valid solution. But there's like many solutions to this problem, and some of them are trivial and others are not. And so a similar problem happens in classification, like when you often have, a classification problem, you have some positives, some negatives, and you have like many classifiers that could work, right? And so if I was to choose between all of these classifiers, which of them would I choose?
Well, the SVM chooses the one with the maximum margin.
Maximum margin, right? So an easier way to think of the maximum margin is like, let's think of this thing, right? There's many things. The margin is basically the distance from, let's say you have a linear classifier. It's the distance from any point perpendicularly to the linear classifier, right? And your margin is the minimum of these distances to your classifier, and you want the margin to be as large as possible, right? And so SVM is a technique, SVMs are techniques to get robust classifiers because they tell you your classifier basically has the biggest distance from all of the points. Right? And so we're going to try and use the same logic here for inverse RL. We're going to say, this is going to be an ambiguous problem. Instead, let's try to say that you want to find a W such that your like W transpose of your expected features under pi star is better than W transpose of expected features under pi plus some margin, right? So you can kind of think of this as, this is kind of like your linear classifier, right? So you're like, in your linear classifier, you're going to have like y is equal to W transpose x plus p, right? It's a similar deal. But you want this to have a margin, which means that like the features under pi star are better than the features under pi by some amount, right? And you want to like maximize the amount, right? So what that essentially does is it like says that there's many different possible classifiers. You're going to choose the one that has the biggest margin from all the other policies, right? So you're going to say like, these are all policies that you could possibly have. You want to choose the W that assigns the biggest margin across all the policies. So you won't get the trivial solution here, right? Because the trivial solution will give you like 0 margin. Does that make sense? So the only change we're going to make is we're going to try and say, let's pick the W let's pick the W that leads to the biggest margin. Right? And we're going to treat it just like an SVM. So you're going to have some positive labels, some negative labels. In this case, it's going to be expert and non-expert, right? And you're trying to classify between expert and non-expert. And you're trying to find the classifier, which in our case is the reward weights, right? The W's that maximize the difference between the expert and the non-expert for all policies. Does it make sense? Okay, so what do? We said that inverse RL says reward under your value under your expert is better than value for all other policies. We said there's an ambiguity problem. Instead of just solving this constraint, we're going to add a max margin version. So we're going to try and say, let's maximize the margin such that the expert is scored better than all the other policies. And so you're going to try and find the solution to both M and W star, right? Or W here. Looks a lot like an SVM. And I'm not going to go through this math here. You should go look at Andorang's notes. They're excellent. But essentially, just like you were saying, you can like impose a W norm equal to 1 constraint. And this objective you can show that it's equivalent to this objective. So you can show that the max margin objective is the same as like minimizing the W norm, such that W transpose of expert features is greater than W transpose of all other policy features plus 1. And so you can kind of think of this is like constraining the W norm. And so like you can show that this and this are the same objective. Just by using the same logic as SVMs. So what we did here is we said we had this problem which had ambiguity. We converted it to max margin problem. From max margin problem, we convert into a simple thing that we can throw like a linear solver at. Right? So an LP solver you can use to solve this thing. What are the issues with this formulation? And so we've said expert is better than every other thing by a margin. What could go wrong with this?
There's not a good linear function that can actually separate.
Okay, yeah. So like there may not be a good linear solution. So your features might be wrong. So I think in at least a lot of the early RL work, you assume that the true reward function is linear. And so we kind of discount that by assumption. But some of the issues are that this kind of like says that you have to be like uniformly good across all of the policies. Whereas in some cases, you might want the margin to be bigger than others, right? So this is saying this is just treating all policies as equal. And whereas you might want some policies to be bigger margins than others. If you know some policies are just terrible, not the expert policy, some of the other policies. If you know some policies are terrible, you want the margin to be bigger. So you don't want a uniform gap across all pi and pi star. And your expert may not be optimal. Right? So if your expert is not optimal, it's kind of like having a classifier where you have like one of these points go over here. Right? And so your problem may not be perfectly linearly separable. And if your problem is not linearly separable, this thing is going to get totally messed up. Right? And so the problem is if you're not perfectly linearly separable, your margin gets tiny. And you're like, you can't satisfy these constraints. Right? Imagine that you like, as Matthew was saying, if you have like something going over to the other point, to the other side, there's no classifier that can solve the problem. And so this paper max margin planning basically tries to make two changes to the max margin formulation. So the max margin formulation converts inverse RL to solving this constraint optimization. It makes two changes. The first is that you're going to add a structured margin, which says that rather than the margin just being one, as it is for all policies here, you're instead going to have the margin be something that depends on the particular pi. Right? So if you know things about your problem, you can kind of like inject that into the structured max margin, where you can say that the difference kind of depends on how good or bad that particular policy pi is. If you have expert knowledge. And then the second one is that you introduce a slack variable. So you say that like, I allow some things to, break the margin. And you can see that there's some things that like break the margin, like some things that go into the margin. And you just want you don't want it to penalize, you don't want it to break the margin a lot, right? So you say, I'm going to put in a slack variable, and then I'm going to penalize the slack, right? So you're going to say, I'm going to allow some amount of, what do you call it? Encroachment into the margin, right? So the margin is the difference between your classifier and all the points you're trying to classify, right? So you're trying to say that in case of some suboptimal demonstrations, I'm going to allow some things to be better. Some other policies to be better than the expert, but I don't want it to happen a lot. Right? So you're going to allow for some slack, but you're going to penalize the amount of slack that you. And so the logic we took is we said W transpose, this thing is better than this thing. Inherently ambiguous. We convert it into max margin. Max margin is too strict for real world data. And so we make two changes. One is the structured max margin. The second is the slack variable. The slack variable says that this constraint is no longer super tight. You're allowing it to violate the constraint by some amount. You just don't want it to violate it a lot. And the choice of C determines how much you violate your constraint. And so that's all that this paper really does. It just makes two changes to max margin. So it just adds the slack variable and structured max margin. Okay, yeah.
I'm guessing this paper was written after everyone was really familiar with kernel methods. So why not a kernel method here? That
I guess this would be your kernel, right? Like this is kind of your kernel that tells you like the similarity between pi and pi star. And so it tells you how much you should, like you could also do kernel SVM. So you can like I guess if you wanted to make this non-linear, you could do kernel SVM.
Right.
But like the analog to a kernel here would be like how similar pi and pi star to like structure your slack. And if you want to make it non-linear, then you can just do kernel SVM instead of SVM. And that's how you would make it work for non-linear
I
systems.
guess that's what I'm asking, because kernel SVM was all over the place.
Yeah. Yeah, so I think the practical versions of this, they derive it from a linear perspective, but the practical version would use kernel SVM.
Okay.
But do you evaluate this or optimize this over all policies?
Yeah, that's a good question. I'm just gonna go over this. Do I have it here? Okay, yeah. That's one question. Basically, the way you're gonna try and optimize it, you're gonna start with a random policy. You're gonna try and enforce this constraint with your current policy, or like under your current pi naught. Then you're gonna try and find, like, you're gonna get a W. You're gonna take the W and you're gonna try and find an optimal policy under that W. Right? And then you're gonna add that pi back into your constraint set. So it's just like incrementally building up your policy set. So essentially you start with one pi naught, you find something that satisfies this, or basically just one pi naught, right? This will give me like a W, and a W fully specifies a reward. right? Then you take that reward, you run RL on it. RL gives you a policy. You take that policy, you add it back to yourself. Okay? And so you're like mining for constraints. And so it's kind of like playing whack-a-mole in that you start with a policy, you say I have to be better than this policy. It finds something that's better than this policy, and you have to say I have to be better than that policy too. And so you find the most likely best thing, and you say I have to be better than that, have to be better than that, have to be better. And so at convergence, you're just going to have like all possible policies. But usually in practice, you like run it for a reasonable number of policies. Perfect.
One thing what we know in the previous formulation where we don't have to minimum W, like the maximizing formulation there. I feel that like I could keep doing that W as much as I
Yeah.
can and then get very high.
Exactly. So this formulation, what this formulation tries this formulation doesn't like as Mohammed was saying, it's like basically puts a one norm constraint onto W, right? And so like the way to go from here to here is to basically there's a scaling issue. Like you could just blow up your W arbitrarily and it still points in the same direction. And so then this problem is kind of underspecified. And so you have to like put a W norm equal to one constraint here.
And then you take it.
And then what you do is, you can divide this by W norm. And then once you divide, you have max of 1 over W norm. And then you can make that like a min over W norm. Like that's how you're right that this problem is underspecified. So really you want to have a W norm equal to one constraint here. And then you can like convert this problem with a W norm equal to one constraint into this thing, which doesn't allow for the scaling because like it's trying to minimize the W norm. Good question. Good catch. Okay, so all that we did was we added 2 changes to max margin or SPM. We added a structured max margin. We added a slack variable. If you want to make it nonlinear, we could do kernel SPM. But the overall algorithm looks something like this. It's saying, let's propose a reward function, which is linear. We're going to optimize our policy against that reward function. We are then going to try and solve this max margin planning objective to find the next best W, right? Next best W will give me a policy set. I take that policy set, I add it to my constraint set, and I repeat, right? So this might be a better way of explaining it. You start with a random policy pi naught. You then have your constraint set be just pi naught. You solve for the best W. You then solve for the optimal policy under your current W. It gives you some pi I plus 1. You add it to your constraint set. Now you have a different optimization problem with another constraint. You repeat, and you keep going, right? And so you have some termination criteria, how many policies you want, how much you want your margin to be. And then finally, out comes a W and a corresponding policy, right? So W characterizes my reward function, and I have my policy that is corresponding to RL of that reward, right? So the result of this procedure is both a W, which is my reward is W transpose pi. It gives me a reward function and a policy, which is basically the optimum policy under my reward function and my transition. Okay? Yes.
So this is very sensitive for the initial 0, right?
It can be, yeah.
And does it make sense to keep like specifically 0? Because you want your constraints to be specified for 0 also at every time step. So if your initialization is bad, then
But the constraint is basically just it's actually like I would expect the other way around. So like if your initialization is bad, then this is like a trivially easy constraint to satisfy, right? Like basically you're just saying like I only have to be better than pi 0.
yes.
Right? And so that's like a trivially easy one to have. And then the hope would be that you get something that's a bit better than pi 0. And then you add that in, and now you have to be better than both pi 0 and pi 1. And then you add that in, and you have to be better than both pi 0, pi 1, and pi 2. Right? So it's not that, like, I would expect that if pi 0 was actually perfect, then that's like a harder constraint to satisfy. Does that make sense? Okay. So the result of this procedure is an optimal reward function and a corresponding optimal policy. Right? And so this is some videos showing this in action from my PhD advisor back in like 2005 or something. But they're doing apprenticeship learning, which is inverse RL at Stanford with this helicopter doing tricks. So they had like a bunch of like helicopter pilots do tricks with this helicopter, and then they had it essentially run an algorithm very, very similar to this to kind of give you what you're looking for. Yeah, so this was with things that were linear or kernelized, and basically, I think a QP solver, like something that's like no deep nets anywhere. So yeah, this is just doing yeah.
That's a very good way to demonstrate the power of the algorithm. Like you start with the video inverted, so if people think, oh, it's a helicopter flying, it's like inverted. Yeah.
Yeah, it's a
You
cool.
really make a point.
It's a cool demo. Maybe yeah. But
Why in this helicopter example, why is the reward unknown? Why this problem for rewards are compared to what?
so I guess imagine that you were doing a particular trick, right? You're trying to like, you're not just trying to fly straight. You're trying to do a trick which is like a loop-de-loop. Like you have to like maintain this pitch while going in a circle and like come back around, right? And so how would you write the reward function for this? So imagine there's like a trick that you have to demonstrate. How do you write reward functions for tricks? Like it's easy to write reward functions for going straight and going back. But the examples that they actually showed in their paper were more like doing loops and doing tricks and doing S shapes and doing things that are harder to write reward functions for. So that's the idea.
There's a bit more nuance, which is like you could define a trajectory for
Sure.
the trick, but the problem with an enter is like how do you actually, because like the trick is not just like do the S shape. The trick is do the S shape in this orientation, because those helicopters can actually have arbitrary orientations.
I mean, sure, but like the point, I guess, of IRL is that you have to generalize the use.
I'm saying like even if you define the path,
Uh-huh.
the reward is still like not as.
I see. Yeah, that makes sense. Does that make sense, Prem?
Can you repeat the last thing? Even if you define.
Even if you define a path, the helicopter can take that path in many different orientations. Like it can go like this, it can go like this. It can fly in many different ways, especially those kind of helicopters. So it's not easy to define the reward as simply like follow this path, because there are many ways in which you could follow that same path.
I think it makes least sense in a straight line setting, but when you're doing anything else, like Sid is saying, like which is a little more non-trivial, it's not clear how to write that reward function so that like a loop works if it's a small loop, if it's a big loop, if it's a loop here, if it's a loop there, they're all loops, right? So how do you characterize a loop? What is loopiness, really? I think that's what the IRL stuff is trying. Good point. Good.
So I haven't taken a convex optimization course, but is that a convex procedure?
Yeah. Because you have all linear constraints.
Okay, so how is D structured?
That's a good question. I'm sure that it's convex, but I don't actually know what they use it for. I can look into that in fact. But yeah, they would use like a CVX type solver. They would use like an off-the-shelf convex solver.
So another quick question, could you generate a bunch of alternate pies if you started with pi star and added some diffusion, just
You could.
kind of generated a bunch of them?
Yeah.
Because those are all be nearby, but they can get arbitrarily far away.
Yeah. That's a good idea.
Um,
So yeah, you could expand your constraint set way bigger, way quicker.
yeah, instead of going through the iterative process, which is more.
Exactly. Yeah. Because that has to be true for all pies, so you might as well put it at 3 pies. Yeah.
Yes. Okay.
Okay, so that was max margin planning, right? So the idea of max margin planning was the value under R of pi star is greater than the value under R of pi. And we said this was ambiguous, so we added a margin. The margin had some issues. We added slack, and we added a structured margin. That's it. Okay. So all that max margin IRL is it's saying this is the basic logic, and then we just applied a few fixes to it. So this was to deal with ambiguity. This is to deal with suboptimal demonstrations. So if you look at any real human data set, you always have some suboptimal demonstrations, and so you don't want to you don't want to have a really strict margin because you're not like some people will give you bad demos. Okay. Does that make sense? So why is this not, what we do in practice today? Some issues, right? So firstly, there might be some scenarios where the margin is pretty small, as in like some of the other pies that you might get are like pretty close to pi star. And so it's hard to like choose that D carefully. But I think the one that is most problematic is that we're solving this constrained optimization problem, and with a big neural net and nonlinear functions and so on, it's like kind of a pain to solve a constrained optimization problem. And especially when the number of constraints becomes huge, right? So like every policy you have to have a constraint, the number of possible constraints is huge. So solving this kind of becomes a pain with like modern function approximation and so on. And so the next idea is trying to propose a method using maximum entropy, which is easier to solve with gradient-based optimization and not convex solvers. Okay, so one aside we're going to do is this thing called feature matching. And so what feature matching, and then we'll get to maximum entropy. So what feature matching says is that if I have two different policies, let's say pi star and phi, right? If rather than focusing on the reward function, if you can match the feature expectations, then the policies will be similar, right? So that's arguing that like let's take the value of these two policies under some reward function R, right? Let's say the reward function R is again linear. W transpose phi. So then we can substitute in R as linear into here, right? And so you can get this again. This is the same derivation we did earlier. So we can show that R is a value is equal to W transpose of expected features minus W transpose of expected features. Right? The same logic we did earlier. We just stuck in R as W transpose phi, R as W transpose phi. Good. And so we can see that the difference in value between V pi star and V pi R is W transpose of expected features under pi star minus W transpose of expected features under pi, right? Now you can write this as W transpose mu pi star minus mu pi. Right? And just by Cauchy sorts, you can then write this as you can say that like this thing is less than or equal to the W norm times the difference in feature norm. And so what this allows you to say is like value difference is equal to W transpose times feature difference. And W transpose times feature difference is less than or equal to the W norm times the feature difference norm. And so it's arguing that if W norm was less than 1, then and feature norm was less than epsilon, then you can say the value difference is less than epsilon. Right? And so what this is saying, essentially intuitively, what you can think of this as saying is that if the expected features are close enough, right, then the value functions are close enough, or value functions are close as long as the W norm is bounded. And so it's saying that like two policies whose expected features are similar will have similar values. Right? So rather than having to like get a reward function, you can also try and just match features. Right. So if like you have two different policies, you can show that their value difference is bounded by epsilon, where epsilon is their feature difference. Yeah.
So when you say two different policies, are you just like taking like one trajectory from your data set and another trajectory from the data set, or like?
It's more like let's say you had like your expert policy, like let's say a policy was like actually something that goes from state to action. And so you're not just taking single trajectories, it's more like you take the average features under your policy. So in this case, the way you compute this is you average the features that are computed in your demonstration data set. So you're assuming that this expectation comes from your demonstration data set. So you can get this by just averaging features in your demonstration data set. This thing you estimate from your current policy. So it's not like one trajectory, it's more like a expected of many trajectories. Okay, so what does this kind of mean? Let's imagine that your features were things like distance to the object, end effector position, object orientation, things like that. If I have two trajectories that kind of have similar expected sum of features of these things, the argument is that their behavior is roughly similar. Right? But the problem with this is that it's inherently ambiguous. You could have like many different ways of having the same average features. You could have one thing that matches the path, and another thing that like does a bunch of crazy stuff, and then just goes to one state, which has like enough features to compensate for all its suboptimal behavior. Right? And so this problem is inherently ambiguous. And so the idea behind maximum entropy IRL was to say, rather than just doing feature matching, so feature matching says if you have demonstrations, your policy and your policy and your demonstration should at least match in features, right? So it says that like it's saying that if I have these are my feature expectations from my demos. These are my feature expectations from the policy that I'm trying to optimize. But at least they should match in feature expectations, but that's not enough because they're ambiguous. And so what Maxent IRL says is that like, let's try and do feature matching, but let's try to do it with maximum entropy, right? So what it says is let's try and, let me try to work this out. It's trying to say, let's say you have mu of pi star, which is the feature expectations under pi star. So you have mu of pi, right, which is the feature expectations under pi, right? There's like many possible mu of pi's that can match mu of pi star. Let's choose the one that has maximum entropy, right? So it's like the idea is basically the same as similar to robust SVM. It's saying that when there's ambiguity, pick the one that like hedges its bets the most. Like pick the one that is maximum entropy, so it weights good trajectories high, but on all other trajectories, it's as equal as possible. So when you have something that's maximum entropy, it tries to like, be good where it's good, and everything else is weighted exactly the same. Right? So you try to be as uniform as possible. And so the logic behind maximum entropy IRL was that you want to do feature matching, but you want to do it with maximum entropy to deal with ambiguity. So you want to find the trajectory distribution that matches features, but is highest entropy. Okay, so it's a little different than max margin planning. Max margin planning is trying to solve this convex optimization. Like the way to think about maxent IRL is that you're going to start from feature matching. And so you want mu of pi star to be approximately equal to mu of pi, where pi is the policy you're trying to optimize. But you want this to be maximum entropy. Yeah. And it's not obvious how this is going to give us a reward function, but I'll get there in a second. Okay. So let's try and write out some notation. Let's say there's a distribution of trajectories P of tau. You're going to have like the feature expectations under P is basically saying if I sample trajectories from P of tau, and I summed up the features along those trajectories, that is going to be my feature expectations under my policy, mu phi. Okay. So it's just going to say, let's say I took a bunch of different trajectories. Each of them had some features. I sum up those features, and then I average them. And that's going to be my feature expectations under my policy. Yes? So the feature expectations under my policy. You can do the same thing for an expert. Let's say you have a bunch of expert demos. You take their features, you sum them up, and then you average them. Right? And so that's going to be my feature expectations under my expert, feature expectations under my policy. Yes? So you can kind of think of this as like features is telling you like what is the state at different points of your trajectory. You want to sum up those things over the trajectory, average them. You want that average to be equal between your policy and your expert, right? And so the maxent IRL formulation is basically this, which is saying that let's try and have a trajectory distribution that matches features with an expert. Right, so let's try and find a P which matches features with the expert. And as we saw earlier, if you match features with the expert, then your value is close to the expert. The P should be a proper probability distribution, which means it has to integrate to 1. And it has to be maximum entropy. Right, so you're trying to find the maximum entropy P, which matches features and is a probability distribution. So that's all that maxent IRL is. It's trying to say, let me find this P, which matches features with the expert, is a probability distribution, and is maximum entropy. So let me just recap the logic, right? The logic is, we started with feature matching, which says that if I average features for pi star, they should be similar to my current policy pi. Problem with that is there's ambiguity. And so we want to find not just something that satisfies this constraint, but maximize the entropy. Right? And it has to be a proper probability distribution. That's it. So feature matching has ambiguity, add in maxent, you get maxent IRL. This is the objective for maxent IRL. Make sense?
Maybe I missed this earlier, but is the features that we're matching, there's like the, can you give us like the logics, I guess, that you sample from to get an action? Or is it more of like a latent variable?
It's more like a latent variable, yeah. So I guess in a way you can think of it as the logits you sample to get an action, because you can think of like if your policy is going from S to like some features, you can like have the last layer is linear. And so you can kind of think of it as logits, but we're not saying our policy is linear, although it also is, but like we're saying our reward is linear. So it's kind of like if you had something that going from like state to reward as a scalar, it's like the second last layer of that. But we're assuming that someone gives that to us. And we'll go from here to something that's not linear. Right.
I have a question.
Yes.
But, what is the constraint?
Yes.
Sometimes that hard to satisfy.
Um,
What if you, policy like this?
yeah, so we're going to convert into some like gradient based optimization. So we're not going to solve a constraint optimization, and we'll try to get as good as possible.
Sure.
Yeah, that's soft off. Okay, so we're going to go through a bunch of algebra. So it's going to be like 10 minutes of pain, but bear with me. It will all make sense. It'll all make sense in the end. Okay, we're going to start from this objective, maximum entropy IRL, saying let's maximize, let's choose a P which has maximum entropy while matching the expert's feature distribution and being a proper probability distribution. So the expert's feature distribution, remember, you just take trajectories, you take phi over them, you add it, and then you average it. You don't actually need to know pi star. You just need like samples from it. Okay, so what we're going to do is we're going to use, constraint optimization. We're going to set up a Lagrangian. Is everyone familiar with Lagrangian? Okay. So if I have a optimization problem, right? So I'm going to do max of some S with some G, or yeah. Then you can like write this as like max min F plus or minus. Sorry, I always say the signs wrong. Max minus W transpose G, where you're trying to do max over X and min over W. Right? So whenever you have a constraint optimization, you can rewrite this optimization into a min-max optimization form. Right? So that's constraint optimization. And so this is often called Lagrangian. This f of x minus W transpose Q of x. It's called your Lagrangian. And you're trying to max with respect to x and min with respect to W. Okay? And so we're going to apply the same thing here with our constraints. So our Lagrangian is going to be something that maximizes entropy. But then you're going to have the constraints come in as Lagrangian terms, right? So you're going to have W transpose mu of P minus mu of pi star. Right? So you can think of this constraint as basically mu of P minus mu of pi star is equal to 0. Right? So you can think of this constraint as integral P tau d minus 1. Right? And so you can rewrite this. You can rewrite this objective as a max min, right? Where you're going to say it's maximize entropy with W transpose mu P minus mu pi star term, where W is what you call your Lagrange multiplier, minus a lambda times integral P tau d tau minus 1, where this is also Lagrange multiplier. Right? Yeah.
Is there any reason why you have decided for the multipliers?
No. No, it doesn't matter because it's an equality, and so it's an unconstrained range. So you can just like write it as minus W. That's fine. Because it has to like be 0. Yeah, I think I did it to make notation easier later. Okay, so we're just going to write out the Lagrangian here, and we're going to go through a few steps. The first step is we're going to flip max and min using duality. And then we're going to go through 3 steps. We're going to solve with respect to P. Then we're going to solve with respect to W and lambda. So which means we're going to take this objective in here. We're going to set it, we take the gradient, set it to 0 with respect to P. We're going to get a solution for P, and we're going to substitute that in and solve for lambda. We're going to get a solution for lambda, and then we're going to substitute it in and solve for W.
This lady similar to the one.
No, it's just like analytically solving the Lagrangian. It's just like step by step by step. So I'm not going to actually, it's not how you're actually going to do it. Is I just want to analytically solve this Lagrangian. It'll give me a nicer solution. I just want to do it one step at a time. Okay, so we're going to start by solving for optimum P. We're just going to solve this inner optimization problem. We're going to get some solution in terms of W and lambda. Then we're going to solve for W and lambda. That's going to give us a max and IRL procedure. Yes? So all we did is we started from that objective. We want to find a P such that P matches the expert, P is a probability distribution, and P is maximum entropy.
Well, couldn't you have like people be negative of this equation and just read it in memorization?
You could. Yeah, it doesn't matter. You'll get the same answer. Okay, so we're gonna take these steps. We're gonna connect the dots, right? So, remember our objective is maximum entropy with these constraints. We convert into Lagrangian. We're gonna start by solving for P. And so, if I wanted to solve for P in this inner problem, how would I do it? I just want to solve this inner problem. I just want to solve a maximization problem. How do I solve a maximization problem? Take the derivative and set it to 0. Okay? So we're just going to go through the pain of that. But basically, we're going to try and take the derivative of entropy plus W transpose mu P minus mu star minus lambda integral P minus 1. Right? And so entropy is minus P log P. And we're just going to expand feature expectation. Feature expectation is W transpose of integral of the likelihood of a trajectory times the feature sum along the trajectory, right? So it's like take every trajectory. This is like the sum of features along that trajectory. You're going to average over many different trajectories and then multiply by W. That is the same thing as you. Right? That is an expansion of mu. It is like average features. This is like the feature of a trajectory. This is the likelihood of a trajectory. This integral is average features. And so we're just going to expand the first and the second term, and then we're going to take the derivative. So you don't have to don't necessarily follow everything. It doesn't matter. Just derivative, but just get the vibes, right? So we're going to try and take the derivative of this thing. We're going to use product rules here. And believe me without proof that this jumps to here, right? Basically, you can show that minus log p tau minus 1. So this thing will basically become minus log p tau minus 1. You can just get this from product rule. This thing will become W transpose mu tau. This thing will become lambda, right? You just show that's equal to 0. Yes? Okay, so do a little more algebra, and you can show that the optimal p tau is x minus 1 plus W transpose mu tau minus lambda, right? So what does this mean? Like let's try to think about this a little differently. We can think about this as p tau is equal to x of minus 1 minus lambda times x W transpose mu tau. Now, which means that p tau, this is like a proportionality term. You can say that p tau is proportional to x W transpose mu tau. right? So all we did was we took the derivative, we set it to 0. We simplified a bunch of stuff, and we saw that the likelihood of a trajectory is proportional to the x of W transpose mu tau. Now, we know that mu tau is basically the sum of features in a trajectory, right? So mu tau is basically the sum of features in a trajectory. You multiply it by W, you can see that this is basically the sum of rewards, right? So W transpose mu tau is basically W transpose times the sum of features, which is the sum of W transpose times features. Because rewards were linear, this is just the sum of them. Right? So what you want to take away from all of this, right? We started, and all this says is that the likelihood of a trajectory is proportional to the exponential sum of rewards, right? And so this is just like what we often call soft optimality. It says that the likelihood that you take a trajectory is proportional to the exponential sum of rewards of that trajectory. So high reward trajectories are more likely, low reward trajectories are less likely, right? If I have like many different trajectories, like this is the highest reward one, it's the most likely, and then as I get lower reward, I'm less and less likely, right? And so you can think of this as like the solution to this mess basically just suggests that P of tau, the likelihood of a trajectory, is proportional to the exponential sum of rewards in that trajectory. Right? So this is what you call soft optimality. So if you remember maximum entropy RL from active critic, it kind of says the same thing. But it's just saying that if you solve this with respect to P, you get P of tau is x minus 1 plus W transpose mu minus lambda. If you remove x minus 1 minus lambda as a proportionality constant, you can say that P of tau is proportional to x W transpose mu, which is proportional to x R. Yes? Okay, so that's the first thing we want to take away, that the likelihood of a trajectory is proportional to x R, where R is the reward of your trajectory. Okay, so the next thing we want to do is now we solve for P of tau. We want to stick P of tau back in to this optimization problem. We solve the inner optimization problem, stick it back in, and then we're going to solve with respect to lambda. Yeah. And so what we're going to do now is we're going to like take this objective, we're going to substitute this thing into here. Yes. And so all of this is just an expansion of this objective. You can think of this as this is your entropy term minus P log P. This is your feature expectation term, W transpose mu. This is your expert feature expectation term, mu pi star. And this is your lambda constraint. This is your like make it a proper probability distribution constraint. And so this is your probability distribution constraint. This is your feature matching constraint. This is entropy. Yes. All we're doing is we're substituting in the value of P tau into this objective, and it's going to give us something nice. Okay, so we're going to substitute in P tau in some places, but not in others, because that'll help us make this derivation easier. But we're going to substitute in like P tau is this, which means that log P tau is just minus 1 plus W transpose mu minus lambda. Log of x is just, they cancel, right? And so this thing is going to just become this guy. And no other substitutions here. So all we did is we substituted in log p tau. Log p tau is just minus 1 plus W transpose mu minus lambda. Just take the log of this guy. Yes. So all we're going to do, I'm just going to get to an objective, which is going to allow us to solve with respect to W, and then it's going to look really nice. So we're almost there, right? So now when I have this objective, do certain things cancel out? Which things cancel?
WDP tau, mu tau, dp.
This guy cancels. This guy cancels. This guy cancels. This guy cancels. Right? Lots of them cancel out. And so the result just looks really simple, right? It's just going to have a p tau dt term minus W transpose of the expert feature distribution plus a lambda term for this guy. Right? And now we want to minimize this with respect to lambda. So all we did is we just simplified this. Oh no. We simplified this, we substituted it in log PT here, and then we substituted in PT down here to get this objective. Right? Just think of it as magic algebra that took us from this objective up here with the solution we computed for PT earlier to this definition of PT. We stuck this down here and we get this objective, which we can solve with respect to lambda. Right? So we're going to get rid of lambda, and then we'll have a nice expression in terms of W, which is going to help us find our reward function. Yep. I'm going to connect it back, I promise. It's going to make more sense. Sorry, give me a sec. Okay, so let's kind of like simplify this a little bit further. You can expand this guy, the first term, out as x minus 1 minus lambda times x W transpose mu. So that's what we're going to do here, right? So the right-hand side is just the left-hand side with x minus 1 minus lambda taken out of the integral because it doesn't depend on anything in the integral. And we're going to call this thing z. Okay, so we're just going to call integral x W transpose mu as z. And now we're just going to solve this whole thing with respect to lambda. So we're just going to take the gradient of this thing with respect to lambda. We're going to set it to 0. Yeah. So we're going to take the gradient with respect to lambda, set it to 0. What that results in is x minus 1 minus lambda is equal to 1 over z. You can just like take the gradient of this thing, take the gradient of this thing, fit them to 0, and you will get this. The final result that you care about finally is that when you substitute everything back in, you're going to get an objective that looks kind of like this. So you're going to have min W of log z minus W transpose mu. Okay. Now, if you remember log z was basically, or z was integral x W transpose mu. So remember our objective is going to be log z minus W transpose mu. And we're going to simplify this to be something that's really nice and intuitive in the next slide. Right? So what did we do in this slide? I know we've gone through a lot of algebra. We solved for P first. So we took P, we substituted in, and we solved for lambda. Right? And we saw that when you solve for lambda, x1 minus lambda is equal to 1 over z, where z is equal to the integral of x W transpose mu over all trajectories. Okay? So let's just kind of like close the loop. We solved with respect to P, it gave us this objective. We solved with respect to lambda, and it showed that our final objective reduces down to min W log z minus mu transpose of expert features. And now we're just going to solve with respect to W. Right? So W is going to be the parameters of our reward function. We're going to solve with respect to W, and that's going to give us an IRL objective. And so we know that z is equal to integral x W transpose mu. And so this objective, minimum of log z minus W transpose mu, you can actually show that it's equal to this objective. So like the easy way to think about this is that you can rewrite this objective as log z minus log x W transpose mu, right? And so you can write this as log z divided by x W transpose mu, and z is equal to the integral x W transpose mu. And so you can kind of think of this minimization as the maximization of log x W transpose mu by integral x W transpose mu. Right? And so this z is often what you call a partition function. But the vibes here that you really need to get is that this is basically it's like a distribution over trajectories where the likelihood of a trajectory is proportional to its W transpose mu. And as we saw earlier, if your reward is defined as W transpose phi, and mu is defined as your sum of features, then W transpose mu is nothing but your reward, right? So all that this is saying is that the solution to find a W is just you solve this objective, which is saying, let's try to say that the likelihood of a trajectory is proportional to exponentiated reward, which is equal to exponentiated W transpose features. And this has to be a proper probability distribution. And so you can show that P of tau is equal to XR by integral X bar, so that it just integrates to 1, right? So we went through all this algebra. Next time you do this, don't go through the algebra. Just think about it this way. When you have whenever you do maximum entropy almost always reduces to saying your likelihood of your trajectory is proportional to the exponentiated reward. If reward is higher, your trajectory is more likely. If reward is lower, your trajectory is less likely. And so when you have a maximum entropy objective, you can say your likelihood of your reward is XR by integral X bar, right? And then all you're going to try and do is do maximum likelihood with this, right? So you're going to say, this is the likelihood of a trajectory. You're going to sample trajectories from your demos, and then I'm going to do maximum likelihood, right? You can do if you do maximum likelihood with this, you get exactly the same objective. And so we went through all of this algebra, but all that it really comes down to is saying that my trajectory distribution is proportional to XR, and I'm just going to do same maximum likelihood, just like I did for supervised learning. Right? Supervised learning always tries to maximize the likelihood of the data. We're just going to maximize the likelihood of the data, but the data likelihood is proportional to exponentiated reward. Okay? And so that's going to give us our IRL objective. So all the algebra basically just simplifies to give us this relationship. And then you're just going to do maximum likelihood. And we'll simplify this in a second. Someone had the hand up. No? Okay. So the way I find it easiest to think about this is you have many different trajectories. You can think of the maximum likelihood model as saying that the likelihood of a trajectory is proportional to the exponential reward. So high likelihood trajectories are more, low likelihood trajectories are less, but none of the trajectories have zero likelihood. So it's like soft optimality. You're not choosing the max, you're choosing the soft max. Right? You can also look at this thing, it's just like the soft max with infinite number of classes. Right? So you're just saying that your likelihood, so the easiest way to derive maxent IRL is actually to start from P of tau is proportional to XR, and then just do maximum likelihood. So you're going to say, I have trajectories from my demonstrations, I sample trajectories from my demonstrations, I maximize log beta, respect to R. That's it, right? And if your rewards are linear, then you can write R as W transpose mu. But you don't have to. You can also write R as anything else, right? But the maxent IRL paper is infinitely difficult to read. This surprisingly is easier than the maxent IRL paper, but it's a very good paper. It's hard to read. But this is how I would write it. But does this kind of make sense? Logically, it's saying that the likelihood of trajectory is proportional to the exponential reward. We're going to try and maximize the likelihood that the expert demonstrations were produced. But we're going to do it under this like soft optimality formula. So the soft maximum entropy formula. And we'll work out what this is. The solution to this is going to be intuitive also. But does this kind of like logic make sense? So in terms of steps, right? We started by that objective. We solved for P. We solved for lambda. We got that objective. Right? You do a little bit of manipulation with this objective. You come to this nice formulation. This nice formulation is just maximum likelihood, where your trajectory likelihood is proportional to your exponentiated loop. That's it. Everyone with me? Yeah. It doesn't matter if you got the algebra. Skip it. You never have to do it again. That's it.
I mean, I guess it's a pretty dumb question, but is it necessary to take a log? Like, you did a soft math. you have to take a log of the sort. Does that make a big difference when I'm not?
Usually when you're doing like, likelihoods, you always maximize the log likelihood. You don't usually maximize the likelihood with the numerical issues. And so, yeah, you'd usually do the log. Okay, so that's what our objective is going to be. Our trajectories are chosen proportional to the reward. We're going to try and find a reward that gives the expert demonstrations high likelihood. Right? The problem with this objective is that there's an integral inside a log. Integral inside a log is just the bane of humanity. And so always avoid integrals inside logs. The problem is that I have to integrate over all possible trajectories. There's infinitely many possible trajectories. This is why they invented diffusion models, to get rid of this log integral thing. But basically, the problem with this objective is that it's hard to solve because of that. It's hard to evaluate this because I have to like take an integral at the bottom. Right? But what we're going to do is we're going to show that the gradient of this objective is nice and easy to estimate, or easier to estimate. And so we're going to do some more algebra, but it's going to be a little better than last time. So this is our objective for max and IRL. We want to do maximum likelihood. We're just going to solve for the gradient of this objective with respect to W. Yes? Our objective is maximize likelihood of trajectories from the expert demonstration set. We're going to take the gradient with respect to W. Yeah. Now, we said it's going to be painful to estimate it, but the gradient is going to look a lot nicer. So we're going to take the gradient. You take the gradient of the first term minus the gradient of the second term. Right? And so help me work through this. What happens with the gradient of the first term? We've done this like a bunch of times before. No tricks. What do we do? Just move it inside. That's it. That's it. Yeah. Just move it inside. And it's linear, right? So it's easy to take the gradient. So what is the gradient going to be if it's linear? Right? Mu. That's it. The gradient is going to be trajectories from the expert of mu of star. That's it. Right? This term is a little more nasty. So let me take the gradient of this term. How do we do it? We have grad log something. How do we deal with grad log? Don't feel shy. It's fine.
Inside the log 0.5.
So you're just going to use chain rule here, right? So you're going to say grad, you're going to say grad log f of x with respect to x is going to be 1 over f of x times grad f of x with respect to x. Right? You're just going to use chain rule. And so your second term, you're going to use chain rule. And so let's try and write it out. Your chain rule will have a 1 over integral x w transpose mu term at the bottom, right? And then you have to use chain rule. So your numerator is going to have the gradient of x w transpose mu. Right?
Times mu.
Times, right? And so, yeah. So, you can kind of think of this as like the denominator is going to be 1 over integral. The numerator you're going to have an x w transpose mu times the gradient of this thing, which as Mohan said is mu, right? Now, the nice part about this is if you think about like this, we said soft optimality says the trajectory is proportional to the x of w transpose mu, right? If you look at this distribution over here, it's exactly the same as this distribution, right? Which means that your second term is also an expectation. And your second term is an expectation under the soft, let's call this the soft optimal policy distribution. Let's call it soft optimal. So it's saying that your first term is going to be expectation of grad w transpose mu. Your second term is going to be minus expectation of trajectories drawn from your soft optimal distribution of grad W transpose mu. So the first one is going to be from your expert, grad W transpose mu. The second one is going to be from your soft optimal distribution, BW of grad W transpose mu. Right? So think about, let's call this distribution, let's call it BW tau. And all we saw is that this thing is just exactly the same, which is BW tau. Okay? And so all that this objective says, it simplifies to something really nice and easy. It just says, you're going to have two terms in your gradient. The first term is a push up term, and the second term is a push down term. Okay? So you can think of the first term as saying, let's push up on things in the data. Right? So let's say we want to like move W in the direction that increases the features in the data. And the second term is saying, if I sample trajectories from my soft optimal distribution, so this is my soft optimal distribution, I want to push those down. And so essentially it's like one thing is pushing you up and the other thing is pushing you down. So the first term is saying increase the likelihood of things in the data. The second term is saying push down everything else. Right? And you're saying that you're going to push down everything else by sampling from your soft optimal distribution. So the way we got here, let's just recap. I see lots of folks. We just took our maximum likelihood objective. Okay. Our maximum likelihood objective when we said p tau is proportional to x W transpose mu. Okay. That was our model for a trajectory. We said we're going to do maximum likelihood. We just took the gradient of that objective. We noticed that this term is exactly the same as this guy. Right? Like this, look at this guy, look at this guy. They're like exactly the same term. Right? And so then we said there's like an expectation here with respect to the expert, and there's an expectation here with respect to this distribution. Right? And so you're going to push up the things from your expert, and you're going to push down the things from this distribution. Right? So this distribution is your soft optimal distribution. You're going to push it down. You're going to take everything from your expert, you're going to push it up. So one nice thing about this distribution is it's like the solution to maximum entropy RL. If you remember SAC from our actor critical lecture, the solution to SAC is this distribution. So SAC, basically, if I can solve SAC, I'm going to take all the trajectories from a solved SAC and I'm going to push them down. And I'm going to take all the trajectories from my data and push them up. Right? So the way you can kind of think about this from the perspective of the whole algorithm is that you're going to like push up on the data. You're going to take your current reward. You're going to solve SAC. It's going to give you some trajectories. You're going to push down on all those trajectories. Right? And so you choose your reward. You solve for soft optimal policies. You push up the data. You push down everything from your soft optimal policy. Right? So you're saying like the final objective after all of that nasty algebra is very simple. It's just saying push up on data, push down on everything from your policy. Right? So the algorithm is start with a W, solve for an optimal policy, take a gradient step on W, which pushes up on the data, pushes down on all the trajectories from that soft optimal policy. You'll get a new W. You resolve for the soft optimal policy. And then you again push up on the data, push down on the soft optimal policy. Right? And so this is push up, this is push down. Right? So for those of you familiar with generative models, this looks a lot like an energy-based model. It's saying that like an energy-based model, you push up on the data, you push down on the negatives. Here, the data is from your expert, your negatives are from your policy. You're pushing up on the data, pushing down on everything else. Does this make sense? Like a much easier derivation is just starting from this premise. If you can start from the premise of soft optimality, which says the likelihood of a trajectory is proportional to exponentiated rewards, you can just do maximum likelihood on this objective. So you can just say max likelihood of trajectories from the expert of log PW tau with respect to W. You solve this, you're going to get you're going to get this objective to. Okay, but the final algorithm is not so hard. In many ways, it's related to max margin. It's like you push up some stuff, you push down some stuff. It's just that you push down the infinite set of trajectories now. So it's like you're going to solve for the soft optimality, sample from there, and push everything down. So in practice, what you'd often do is you like propose a reward, you solve RL, you push down everything there, you like fine tune the reward a little more, you resolve RL, you push down more, and you kind of repeat. And so we'll go over a more practical version, but does this intuitively kind of make sense? So you start from, sorry, where are we at? Oh, we're already at 12. Thanks. So we start from a reward. Let's say it's linear for now. We are gonna then try and solve this objective where we're gonna like increase things in the data, decrease things from our optimal policy. It's going to give us an update to W. So to do this, the place where RL is hidden is inside solving this objective, right? So RL is inside this IRL objective in here. And then you're going to like update your reward function and repeat. So this objective looks like it doesn't have RL, but the RL is hidden inside that second term. And so you propose a reward function, you solve this by solving RL. Then you update your reward function with the gradient, then you have to resolve RL with the new W, and then you repeat. Right? And so that's what maxent IRL does. Okay, there's a lot of algebra, but the vibes are just this. Push up on data, push down on everything else. That's it. And we will make this super practical next time. Thanks, folks.